Welcome to Night Cosmos Sleep. Within the equations used to describe space, time, and gravity, physicists once discovered a strange structure that stands in almost perfect opposition to a black hole. If a black hole is a region where matter and light can enter but never return, then this structure allows everything to escape while preventing anything from the outside from crossing in. It is known as a white hole. So far, no telescope has ever detected and confirmed a genuine white hole in the universe. No specific location in the sky has been recognized as the site of one, and no observed eruption has been distinct enough to prove that matter is emerging from a horizon that opens in only one direction. Yet a white hole is not simply an idea invented for science fiction. It appears naturally when certain solutions of general relativity are extended or viewed with the direction of time reversed. This gives rise to an important question. If mathematics allows a region of space-time that can only release matter and energy, why does nature seem unable to create one? An equation may describe many valid structures, but for any of them to become a real astronomical object, it must have a way to form, survive long enough in a universe filled with light and matter, and leave behind a signature that humans can observe. White holes therefore exist along the boundary between what physics permits and what the universe actually builds. They may be nothing more than the reversed image of a process that is almost impossible in nature, because the universe tends to move from highly ordered states toward increasingly disordered ones. It is also possible that a white hole could appear for only a very brief moment, perhaps during the final stage of a black hole, when quantum effects that we do not yet fully understand begin to alter the structure of spacetime. None of these models has been confirmed through observation, so this journey will maintain a clear distinction between what has been seen, what the equations predict, and what remains only a hypothesis. To understand whether a white hole could be a real cosmic object or merely a reflection created by mathematics, we must first return to the one-way doorway that transformed the way humanity sees the universe. About 26,000 light-years from Earth, near the center of the Milky Way, lies a region almost completely hidden behind thick clouds of dust and millions of tightly packed stars. When astronomers point their telescopes toward it, they do not see a gigantic object glowing in the darkness, nor do they find a clearly defined surface reflecting light back into space. What they see instead are several stars moving at extraordinary speeds around a very small region that appears almost entirely dark. Those orbits are not random. They curve sharply around the same point, like leaves being carried by an invisible whirlpool. Some of the stars take several decades to complete a single orbit, yet as they approach the center, their speed increases dramatically. From these motions, astronomers can calculate that something at the center must possess a mass roughly 4 million times greater than that of the Sun, while all of that mass is confined within a region so small that no ordinary cluster of stars could explain it. This invisible object is known as Sagittarius A. For decades, research teams patiently followed individual stars as they traveled around it, recording their positions, velocities, and the gradual changes in their orbits over time. They did not need to see the central object directly, because its gravity had already left a clear imprint on everything moving nearby. Just as trembling branches can reveal the presence of a wind that cannot be seen, the paths of these stars exposed an enormous mass hidden in the darkness. In 2022, the Event Horizon Telescope released the first image of the region surrounding Sagittarius A. This was not the work of a single telescope, but of a global network of radio observatories spread across the Earth, operating together as though they formed a telescope nearly the size of the planet itself. After years of collecting and processing data, the resulting image appeared as a glowing orange ring surrounding a dark region at its center. That darkness is not a black sphere with a solid surface, nor is it the event horizon photographed directly as a sharp boundary. Light produced by the hot gas near the black hole must travel through a region where space-time is curved with extraordinary intensity. Some rays are bent so strongly that they circle the object before escaping. Photons that pass too close may become trapped in unstable orbits or continue falling deeper inward, never reaching our telescopes. The combination of light being bent and light disappearing from view creates a dark region known as the black hole's shadow. This shadow is larger than the true event horizon because gravity alters the paths of light around it. The surrounding ring is not perfectly uniform either, because the hot gas is moving at tremendous speed. Material rotating toward the observer can appear brighter than material moving away, giving the entire image an asymmetrical appearance. Although blurred and far less detailed than an ordinary photograph, the image carries enormous significance. It shows light behaving exactly as general relativity predicts around an extremely compact object. When this evidence is combined with the motion of nearby stars, the measured mass, and the size of the dark region, the most convincing explanation is that a supermassive black hole exists at the center of the Milky Way. But what exactly is a black hole? The name may bring to mind a hole carved out of space, like an empty dark cavity waiting to swallow anything that comes near. Yet a black hole is not a hole in the ordinary sense, nor is it a solid sphere, pulling the entire universe toward itself from every distance. It is a region of space-time where gravity has altered the structure of the paths that matter and light are able to follow. Outside it, a spacecraft can orbit a black hole if it follows the right trajectory. A planet could circle one just as it would orbit any other object of the same mass. Only when something moves sufficiently close does the difference become decisive. There is a boundary beyond which no path leading into the future can ever return to the outside. That boundary is called the event horizon. The event horizon is not a wall made of matter. It has no surface that can be touched, emits no light, and produces no collision when an object crosses it. If an astronaut were falling into a sufficiently large black hole, they might pass through the horizon without noticing any obvious sign at that exact moment. The instruments aboard the spacecraft would continue to function, time would continue to pass, and no physical door would close behind them. Yet, from the moment the horizon is crossed, every possible path into the future leads farther inward. The astronaut could fire the engines, turn the spacecraft in any direction, or send a beam of light outward, but none of these actions could create a route back. This is not because the spacecraft lacks enough power. It is because the structure of space-time itself no longer contains an outward direction. One way to imagine this is to picture a river flowing toward a waterfall. Far from the edge, a boat can use its engine to travel upstream or move toward the shore. As it approaches the falls, the current becomes faster, forcing the engine to work harder simply to remain in place. At a certain boundary, the water moves so quickly that no matter how powerful the engine may be, the boat will still be carried forward. The event horizon can be understood in a similar way, except that instead of flowing water, space-time itself tilts every possible path inward. Light always continues moving at the speed of light wherever it travels, but every direction available to it now leads deeper into the darkness. Light is not gradually slowed until it stops. It simply no longer has any path that points outward. The size of the horizon depends on the amount of mass compressed within it. For a black hole that is neither rotating nor electrically charged, this characteristic distance is usually called the Schwarzschild radius. The greater the mass, the wider the horizon becomes. But what matters is not only how much material exists, it also depends on how tightly that material has been concentrated into a small region. If the entire mass of the Sun were compressed into a sphere with a radius of about 2.95 kilometers, an event horizon would form and the Sun would become a black hole. If Earth kept its present mass, but were compressed instead, the required radius would be only about 8.9 millimeters, roughly the size of a small marble. These numbers do not mean that the Sun or Earth is on its way to becoming a black hole, because no natural process currently exists that could compress either one to such an extreme. They simply reveal how intensely mass must be concentrated before a region of no return can form. Because their gravity is so powerful, black holes are often misunderstood as enormous cosmic vacuum cleaners capable of pulling everything in the universe toward them. In reality, at a sufficient distance, the gravitational field of a black hole is not very different from that of any other object with the same mass. If the Sun were suddenly replaced by a black hole of identical mass, and we set aside the loss of sunlight and heat, Earth would continue moving along an orbit very similar to the one it follows today. Our planet would not immediately be pulled inward, because gravity at this distance would not become stronger simply because the central object had turned into a black hole. The real difference appears in the region very close to that mass. An ordinary star has a surface and a large physical radius, while a black hole allows matter to travel much deeper before reaching the horizon. The closer something comes, the more violent the effects of space-time curvature and the difference in gravitational pull between nearby locations become. Around many black holes, astronomers observe brilliant disks of glowing gas. Their appearance can sometimes make it seem as though the black hole itself is shining or expelling matter from within, but the true source of that light lies outside the event horizon. Gas and dust drawn inward by gravity do not always fall straight in, because they usually carry angular momentum. Instead, the material forms an accretion disk, spiraling around the black hole at increasing speed as it gradually loses energy and moves inward. Different layers of gas within the disk travel at different speeds, colliding, compressing, and heating to millions of degrees. Before crossing the horizon, the material can release enormous amounts of radiation, especially X-rays. In many cases, the region surrounding a black hole becomes bright enough to be seen from billions of light-years away, even though the black hole itself remains completely dark. Near some rapidly spinning black holes, the magnetic fields within the accretion disk can become extremely powerful and complex. Part of the surrounding material may be guided into narrow streams launched from regions near the two poles at tremendous speed. These jets can extend across distances larger than the galaxies that contain them. But they are not made of matter that crossed the event horizon and then escaped. Everything within the jets was redirected or accelerated while it was still outside the boundary of no return. This distinction is important because a black hole cannot simply open and release whatever has already passed beyond its horizon. The bright streams of matter seen nearby are not evidence of an escape route from within. They only reveal how violently the environment outside the horizon can behave when gas, magnetic fields, and rotation interact. For a long time, black holes existed only as a strange consequence of the equations. Albert Einstein himself did not believe that nature would easily create such objects. Yet over time, evidence began to emerge from many independent directions. Stars near the center of the Milky Way orbit an enormous invisible mass. Binary star systems emit X-rays, as matter is pulled away from one star and falls toward an unseen object. Gravitational wave detectors record ripples in space-time produced when compact objects merge. The Event Horizon Telescope has also revealed shadow-like regions consistent with predictions for light around the supermassive black holes M87 times and Sagittarius A. No single observation tells the entire story on its own, but together they form an increasingly solid picture. Black holes are no longer merely mathematical possibilities. They are astronomical objects with measurable masses, gravitational effects that can be tracked, and surrounding environments that can be studied with many different kinds of telescopes. And from this one-way door, revealed through all of these traces, the equations open the way to a far more opposite possibility. If a black hole is a place where every future-directed path leads inward, what appears when the entire structure is viewed with time running in reverse? No new law of physics is required. Simply allow the film of a black hole to run slowly backward, and another doorway begins to emerge. Imagine an egg resting quietly at the edge of a table. A slight bump is enough to send it rolling off, falling through the air, and shattering across the floor. The shell breaks into many pieces, while the white and yolk spread into a shapeless, disordered mess. When events unfold in the familiar direction, the scene seems entirely ordinary and gives us no reason to question any law of nature. But if the footage is played in reverse, everything immediately becomes difficult to believe. The egg white and yolk scattered across the floor begin to gather themselves together. The fragments of shell slide back into their exact positions and seal perfectly around them. The restored egg then rises from the ground, floats through the air, and settles gently onto the edge of the table, as though the fall had never happened. This is not the same as traveling into the past. No one steps into a time machine and returns to a day that has already passed. We are simply reversing every motion in a recorded sequence so that all events occur in the opposite order. Each fragment of shell still moves through space, and every drop of liquid still follows the laws of mechanics. But all of them must coordinate with almost perfect precision to return to their original state. It is this flawless coordination that makes the reversed footage seem absurd. An egg can break in countless different ways, but there are only a very small number of ways for every fragment to find its proper place and reconstruct the original form. The equations describing the motion of individual particles may sometimes allow us to write the process backward, but that does not mean nature regularly prepares the exact conditions required for it to happen. The image of a film running in reverse also provides the simplest path toward the idea of a white hole. In an ideal black hole, matter and light can travel inward from the outside toward the event horizon. Once they cross that boundary, every path leading into the future carries them farther inward, so no signal can ever return to the surrounding space. If the entire mathematical structure of a black hole is reversed in time, the direction of those paths is reversed as well. Light no longer travels from the outside into the darkness. Instead, it begins within and moves outward. Matter does not collapse through the horizon, but emerges from the region beyond it and then departs along the paths permitted by the structure of space-time. This reversed structure is called a white hole. In the classical description, a white hole is a region of space-time from which matter and energy can escape, but into which nothing can enter. It is often described as the time-reversed reflection of a black hole, because the two structures can be imagined as opposite versions of the same doorway. A black hole allows passage inward but offers no route back, while a white hole allows everything inside to leave but provides no path from the outside in. This description can easily create the impression that a white hole behaves like a magnet with its poles reversed, continuously pushing planets, dust, and gas away. Yet the difference between a black hole and a white hole does not come from some opposite form of gravity. An ideal white hole would still possess mass and would still curve the spacetime surrounding it. From a sufficient distance, its external gravitational field could resemble that of a black hole with the same mass. A planet could still orbit it, a cloud of gas could still be drawn closer, and light could still bend while passing through the region of spacetime shaped by that mass. A white hole is therefore not a source of antigravity capable of repelling everything around it. If an object remained outside and traveled toward the white hole, gravity could still curve its path inward. The true strangeness would appear only as the object approached the boundary known in the idealized model as the white hole horizon. There would be no invisible wall throwing the object backward, nor any solid layer of matter preventing it from crossing. The limitation would lie within the structure of the paths that light and matter are allowed to follow. In a black hole, once something is inside the horizon, every valid future direction leads deeper into the darkness. In a white hole, every valid future direction within the interior leads outward. For an object outside to enter a white hole, it would have to follow a path that does not exist within the causal structure of that solution. It would not be forced back by a power stronger than its engines. There would simply be no future-directed trajectory connecting the exterior region to the white hole's interior. One way to picture this is as a railway station containing only tracks that lead outward. Trains continually leave the station, travel across open fields, and continue toward distant cities. Someone standing outside could still see the station, walk around it, and even approach very close to the entrance. Yet no track would run in the opposite direction to carry that person inside. The station would not need to generate any mysterious repulsive force. The issue would simply be the direction of the entire railway system. Every active line would carry trains from the inside outward, while no incoming route would exist. This image cannot fully represent the geometry of spacetime, but it shows that the boundary of a white hole concerns the directions that are permitted, rather than a force of antigravity. Another common misunderstanding is that matter would have to travel faster than light in order to escape from a white hole. This idea often begins with the fact that a black hole can trap even light, so its opposite might seem to require matter to be launched outward beyond that limit. General relativity, however, demands no such thing. At every location, a material particle still moves more slowly than light when measured by an observer nearby. Light remains the ultimate speed limit of nature. What is unusual is not the speed, but the direction of the available trajectories. Within a white hole region, every path leading into the future points outward, allowing matter to leave without ever exceeding the speed of light. It is similar to a boat placed in a river that flows in only one direction. The boat does not need to surpass any speed limit in order to move with the current. It simply travels along the direction permitted by its surroundings. In a white hole, the structure of spacetime itself guides every future trajectory outward. Yet the symmetry between black holes and white holes is clear only when we consider a perfectly idealized solution. It does not mean that every black hole in the universe stores matter for a time and will eventually open to return everything it once consumed. A classical white hole is not simply a black hole entering a reverse ejection phase. In the time-reversed model, the white hole has its own history located toward the past of spacetime. Matter emerging from it is not necessarily made of objects that previously fell into a black hole within the same history being followed by an observer. The structure is built as a complete solution from the beginning, with a black hole region toward the future and a white hole region toward the past. For this reason, when we observe streams of matter erupting near a black hole, we should not call them white holes. These jets are produced by gas, magnetic fields, and rotation outside the event horizon. The matter within them never entered the black hole's interior and then returned. It was redirected before crossing the boundary of no return. In the same way, an extremely powerful cosmic explosion does not automatically qualify as a white hole. A supernova can hurl the outer layers of a star into space. A neutron star can produce violent eruptions. Hot gas surrounding a black hole can radiate more energy than an entire galaxy. All of these phenomena arise through physical mechanisms operating in ordinary space and do not require matter to emerge from behind a white hole horizon. The idea that a real black hole might transform into a white hole appears only in certain modern models of quantum gravity. These models suggest that the collapse inside a black hole may not continue without limit. Once the density becomes extreme enough, quantum effects within spacetime might halt the contraction and cause it to rebound, creating a phase in which matter could move outward. This is a different story from the classical white hole produced by reversing the direction of time in an ideal black hole solution. It is also not a conclusion that has been observed or proven. At present, there is no evidence that an astronomical black hole has ever transformed into a white hole, and no complete theory of quantum gravity exists to determine whether such a process truly occurs. This distinction brings us back to the important boundary between mathematics and nature. When a structure appears in an equation, it means that the model under consideration does not immediately rule it out, but the equations do not yet tell us whether the universe can create that structure through a real physical process, whether it can remain stable against disturbances from its surroundings, or whether it would leave a signature clear enough for humans to recognize. A blueprint may depict a complete building with symmetrical corridors, precisely arranged rooms, and doors that open in only one direction. But for that building to exist in the real world, it requires materials, a construction process, and conditions that keep the structure from collapsing. Today, a white hole resembles architecture already drawn on the blueprint, while the true construction site of the universe has yet to show that it was ever built. Let us return to the film of a black hole and allow it to run backward once more. A collapsing star appears to begin expanding. Matter that once fell inward now moves outward. Light emerges from the darkness, while scattered clouds of gas gradually return to their exact positions, rebuilding the structure that existed before the collapse. Each individual motion may be written in reverse within an ideal model, but the complete scene demands an almost perfect arrangement. A single particle moving in the wrong direction, one photon appearing at the wrong moment, or even a small disturbance from the surrounding environment could prevent that reversed history from matching the original solution. Mathematics may therefore allow the film to run backward, but whether nature ever plays such a film remains unanswered. To understand a white hole not merely as a reflected image, but as a specific region within the structure of spacetime, we must locate it on the map physicists use to trace the paths of light around a horizon. If a white hole appears when a black hole solution is extended and reversed in time, where does it lie on that map? To reveal this hidden region, physicists must change the way space and time are drawn around the event horizon. On ancient maps, some regions were sometimes left blank or ended abruptly at a sharp boundary. Sailors looking at them might have imagined that the world itself truly stopped at that edge, only to discover later that the limit was not in the ocean, but in the way humans had drawn the map. The uncharted land had always been there. The old map simply lacked the ability to represent it. Something similar once happened when physicists tried to describe spacetime around a black hole. After Albert Einstein published his theory of general relativity, Carl Schwarzschild found one of the earliest solutions to its equations. The Schwarzschild solution describes the gravitational field outside an object that has mass, but neither rotates nor carries an electric charge, while also showing how space and time are transformed near an extremely compact concentration of matter. When the original coordinate system was used, certain quantities in the equations appeared to become infinite at a particular distance. That distance is what we now call the event horizon. At first glance, this result made the horizon seem like a place where the structure of space-time broke down completely, where the equations could go no farther and every physical description had to end. But an infinity appearing in an equation does not always mean that nature truly contains something infinite. Sometimes, the problem lies only in the system used to measure and record positions. On the surface of Earth, lines of longitude remain widely separated near the equator but converge as they approach the poles. At the North Pole, longitude becomes difficult to define because every line meets at the same point. This does not mean the ground at the pole has been torn apart. It simply means that the coordinate system is no longer convenient there. Physicists gradually realized that the event horizon in the Schwarzschild solution might involve a similar problem. It was not necessarily where space-time itself came to an end, but rather a boundary where the old coordinates could no longer describe what was happening clearly. By changing the way the map was drawn, light and matter could be followed across the horizon without encountering an artificial break. Several new coordinate systems were developed for this purpose. In 1960, Martin Kruskal published a representation that allowed the Schwarzschild solution to be extended more completely. On this new map, the event horizon was no longer the edge of the world. Space-time continued into regions that the earlier coordinates had concealed, like an expanse of ocean appearing after the map had been redrawn. The Kruskal diagram is often shown as a large diamond divided into 4 regions. It is not a map of space in the ordinary sense, because each point represents an event, meaning a position combined with a moment in time. The axes do not merely show where an object is. They also indicate when it exists and which directions it may travel toward in the future. A region on the right represents the exterior of the black hole, where an observer could remain at a safe distance, watch matter orbiting, and follow light as it bends. This is the region most closely resembling. On the opposite side lies a second exterior region with a similar structure, yet separated within the mathematical solution. These 2 regions are not 2 locations that humanity has observed in the sky. They are parts that appear when the solution for an eternal black hole is extended as fully as possible. The upper portion of the diamond is the black hole region. Once an object crosses the horizon from the exterior and enters this area, every future directed path leads toward the singularity. The object may try to change direction, emit light, or use any engine imaginable, but no choice can return it to the outside. Within this region, moving toward the future also means moving farther inward. The lower portion of the diamond is the white hole region. There, trajectories do not end at a singularity in the future. Instead, they begin at a singularity located in the past. Matter and light leave this region and travel into the 2 exterior domains. No future-directed path allows an object from the outside to travel backward into the white hole. The difference between these 2 regions does not require complicated formulas to understand. It is enough to imagine that light and matter cannot freely choose every possible direction through space-time. At each location, the surrounding structure permits only certain paths into the future. The way those paths tilt across the diagram reveals where an object may travel and which regions will remain forever beyond its reach. Inside the black hole region, every future direction leans inward, like roads on a mountainside that all descend toward the same valley. A traveler may move quickly or slowly, veer left or right, but no road leads back toward the summit. In the white hole region, this picture is reversed. Every path begins in the deep region below and opens outward, while no route allows someone outside to return to the point from which those paths emerged. On this map, the white hole has a clearly defined location. It is not added through a separate hypothesis, but appears as the time-symmetric counterpart of the black hole within the maximally extended Schwarzschild solution. If the upper region describes a place where every future trajectory moves inward, the lower region describes one where every future trajectory moves outward. This is also where we must distinguish between a complete mathematical map and the actual history of an astronomical object. The Kruskal diagram describes an eternal black hole, meaning that the structure has existed from the infinite past and continues into the infinite future within a perfectly idealized model. It does not begin as a living star, nor does it form at a specific moment after a collapse. In this solution, the black hole region, the white hole region, and the two exterior domains all coexist as parts of one complete structure. The symmetry makes the map elegant and clear, but that very perfection also shows why it does not necessarily describe how real black holes are born in the universe. A real star has not existed as a black hole since the infinite past. It forms from a cloud of gas, shines for millions or billions of years, and only then approaches the final stages of its life. As the fuel in its core is depleted, the star may lose the ability to resist gravity and begin to collapse. If the remaining core is massive enough, an event horizon forms during that process. This history has a definite beginning. Before the star collapses, the surrounding space does not contain a white hole region ejecting matter. Only after the material contracts sufficiently does the black hole region appear toward the future. A map describing a black hole formed through stellar collapse, therefore, does not look exactly like the symmetrical map of an eternal black hole. In a realistic astronomical case, the classical white hole region does not automatically appear. There is no past singularity expelling matter in preparation for the existence of the star. Instead, the material already existed outside, gathered together to form the star, and then moved inward as the collapse unfolded. The horizon emerges through a process directed toward the future, rather than from a structure already laid out across the entire history of space-time. The difference can be imagined through two houses. The first exists as a complete architectural plan, with two symmetrical doors at opposite ends and every hallway drawn in advance. Looking at the blueprint, we see the entire structure at once, from the entrance to the exit. The second house is gradually built through real history. At first, there is only an ordinary room. Later, a new hallway is opened, and eventually a door appears that permits passage in only one direction. The fact that the ideal blueprint contains two symmetrical doors does not mean that the building constructed in reality must contain both. The construction process may create only part of the structure permitted by geometry. This is why the appearance of a white hole in the Schwarzschild solution is not enough to prove that white holes exist in the universe. The equations show that such a structure is valid within a fully extended model, but they do not also provide a natural process capable of creating it. The map tells us that the white hole region can be drawn. It does not tell us that a star, an explosion, or any other real astronomical phenomenon can actually build it. This distinction also explains why physicists do not assume that every part of a mathematical solution must correspond to an object that exists. An equation may contain many possible histories, but nature selects only those consistent with the initial conditions, the matter available, and the evolution of the universe. A structure that appears symmetrical on paper may become asymmetrical when placed within a specific history. A black hole has a fairly clear formation history. Matter begins outside, is drawn inward by gravity, and grows increasingly dense until a horizon appears once the collapse becomes sufficiently extreme. This process does not require the entire surrounding environment to be prepared with absolute precision. Stars with many different masses and internal structures can still reach a similar end if their cores are heavy enough. A white hole, by contrast, requires a reversed history. Matter must begin within a hidden region in the past, emerge along exactly the required trajectories, and prevent anything from the external environment from entering. The fact that this region has a place on the mathematical map does not explain where it came from, why its initial conditions were arranged with such precision, or how the structure could survive in a universe that is never perfectly still. From this point onward, the central question begins to change. The issue is no longer whether Einstein's equations contain white holes, because the answer within the extended solution is already fairly clear. What must be explained is whether the universe possesses a physical mechanism capable of creating a white hole region in the same way that gravitational collapse creates a black hole. If a white hole has a clearly defined place on the mathematical map, why does the death of a star open only a doorway inward without also creating a doorway outward? To answer that question, we must leave the idealized map behind and follow the real history of matter as a star begins to lose its ability to resist its own gravity. For most of its life, a massive star exists in a state of balance between two opposing tendencies. Gravity continuously pulls matter toward the center, while energy produced by nuclear reactions heats the core and creates outward pressure. Through this constant struggle, the star can maintain a relatively stable size and continue shining for millions of years. Massive stars consume their fuel far more quickly than the Sun. As the hydrogen in the core is gradually exhausted, they continue fusing heavier elements through several stages, producing a structure resembling the layers of an onion. The heaviest elements lie deepest within the star, while lighter layers remain farther outside. Eventually, this process creates an iron-rich core, but fusing iron no longer provides a useful source of energy to resist the enormous weight of the material above it. As that support weakens, the core may collapse within an extremely short period of time. The outer material loses the foundation beneath it and begins falling inward, while the density and temperature at the center rise violently. In many stars, the collapse produces a shock wave, aided by processes occurring within the core, which then blasts the outer layers into space in a supernova explosion that may briefly shine as brightly as an entire galaxy. What remains after the explosion depends on the star's mass and evolutionary history. Stars born with more than roughly 8 times the mass of the Sun may undergo core collapse, but not all of them form black holes. Some leave behind neutron stars, while more massive stars, according to NASA's approximate classification, may produce stellar mass black holes if their cores continue contracting. The exact boundary is not fixed, because it also depends on how much material the star has lost, its chemical composition, its rotation, and whether it has a companion star. If the remaining core is not too massive, pressure within neutron matter can halt the contraction, creating a neutron star only about as wide as a city, yet containing more mass than the Sun. When the core exceeds that limit, no force known in classical physics can keep it stable. The matter continues to compress, an event horizon forms, and the interior region gradually becomes cut off from observation by the outside universe. The history of the matter during this process is clear. At first, it lies within the layers of the star, outside the region that has not yet become a black hole. When reactions in the core can no longer maintain the necessary pressure, the material begins falling into an ever smaller volume. At a certain point, the contraction creates a boundary beyond which light can no longer find a path back outside. Not every black hole born from a star must be accompanied by a brilliant explosion. In some cases, the shock wave may not be powerful enough to drive most of the outer layers away. Material that was briefly lifted outward falls back again, adding mass to the newly formed black hole. This process is often called a failed supernova or direct collapse, although its precise details are still being studied. One well-known case is N6946 BH1, a massive star in the galaxy NGC 6946. It brightened in 2009, then gradually faded and had nearly disappeared from visible light by 2015. Observations from Hubble, Spitzer, and the Large Binocular Telescope suggest that it may have collapsed directly into a black hole without producing the luminous supernova normally expected. Astronomers still describe it as a candidate, however, because directly observing the moment an event horizon forms is extraordinarily difficult. Archived data from the NEOWISE spacecraft later helped researchers follow another case known as M312014DS1 in the Andromeda Galaxy. This star once became brighter in infrared wavelengths, while its visible light declined by more than a factor of 10,000 over the following years. The researchers proposed that its core had collapsed, while the shock wave remained too weak to expel the entire star, causing most of the material to fall into the newly formed black hole. This is a remarkable observational clue, but it is still evaluated through changes in the star's light rather than through a direct image of the event horizon. These examples show that the universe may create black holes in several different ways. A star may explode and leave behind a collapsing core, or it may fade almost silently as most of its material falls directly inward. Although the outward appearance differs, the fundamental direction of motion remains the same. Matter travels from the exterior into an increasingly dense region. This process follows the familiar direction of time in nature. A complex structure gradually loses its ability to sustain itself. Matter becomes more concentrated, and energy is released into the surrounding environment. A star does not need to be prepared in a perfectly precise state in order to collapse. As long as the core is sufficiently massive and pressure can no longer resist gravity, the contraction can continue on its own, even if the motion of each layer is not exactly the same. A classical white hole, by contrast, would require an almost completely reversed history. Instead of matter collapsing inward from the outside, a quantity of matter would have to emerge from a region hidden in the past and spread outward. Its particles, photons, and streams of energy would need to be arranged so that the entire structure matched the time-reversed image of an ideal black hole. Not only would the escaping matter need to be in precisely the right state, but the surrounding environment would also have to be specially prepared. No stream of gas, particle of dust, or ray of light could be allowed to disturb the carefully arranged history. Even a tiny disruption that did not belong to this reversed film could prevent the structure from matching the original solution. The difference can be imagined through a building that is losing its structural integrity. When an important support column breaks, the upper section begins to fall. Walls, glass, and electrical wiring may collapse in many different directions, but every path leads toward the same general outcome as the structure falls under gravity. If the film were played backward, every fragment of concrete would have to rise from the ground, fly into its exact position, and reconnect with the surrounding pieces. The glass would have to return intact to its frames, the electrical wires would need to reconnect themselves, and the entire building would have to rebuild in precisely the correct order. The equations governing each fragment's motion might be written in reverse, but the chance of everything spontaneously arranging itself with such accuracy would be almost impossibly small. A classical white hole would demand a similar degree of preparation. It would not merely be an object ejecting matter into space. The entire past of that region of space-time would need to be arranged so that nothing could enter, while everything emerging from it followed a very specific history. That is something the collapse of a star cannot create on its own. As a stellar core contracts, matter moves from the outside inward and forms a black hole region toward the future. At no stage in that history is matter required to emerge from a past singularity and spread outward. The idealized map may contain a white hole region, but the real astronomical process constructs only the portion corresponding to a black hole. This also helps distinguish a white hole from a supernova. During a supernova, matter truly is expelled at enormous speed, but all of that material already existed within the star before the explosion. It is accelerated by a shock wave and by processes unfolding as the core collapses, rather than emerging from behind a horizon that permits passage only outward. The event is therefore not the reversed film of a dying star. While the outer layers fly away, the core may continue contracting inward. Both directions of motion can appear within the same explosion, but together they do not create the causal structure of a white hole. Quasars are also sometimes mistaken for white holes because of their extraordinary brightness. In reality, a quasar is an intensely active region surrounding a supermassive black hole that is drawing in gas. The material forms a rotating disk, where it is compressed and heated before crossing the horizon, allowing it to release enough radiation to outshine the entire rest of its galaxy. Jets extending across thousands or even millions of light-years are also not evidence that matter has escaped from a black hole. Magnetic fields and rotation near the black hole can channel part of the surrounding gas into two narrow streams launched from regions near the poles. The material within them is redirected while it remains outside the event horizon, so it never enters the region from which return is impossible. Extraordinary brightness or energy is therefore not enough to confirm the presence of a white hole. The universe has many ways to produce supernovae, gamma-ray bursts, quasars, and jets without requiring a horizon that opens only outward. To identify a white hole, astronomers would need to find a signature directly connected to its spacetime structure, rather than merely an unusual eruption. Beyond stellar collapse, black holes can also grow and create larger black holes through mergers. On the 14th of September 2015, the two LIGO detectors recorded the signal GW150914, produced when two black holes with masses of about 36 and 29 suns spiraled together and merged roughly 1.3 billion light-years away. The final object had a mass of nearly 62 suns, while energy equivalent to about 3 solar masses was carried away in the form of gravitational waves. This event provided direct evidence that binary black hole systems can exist, merge, and create larger black holes. Since then, many other mergers have been detected, opening a way to observe black holes without relying on light. What is especially important is that throughout the entire process, the gravitational waves revealed two objects moving inward toward one another and forming a single gravitational region. There was no phase in which a white hole appeared and expelled matter outward. The central issue lies in the difference between a mathematical solution and a formation process. Mathematics may describe a complete structure containing a black hole region, a white hole region, and symmetrical domains of space. But for any part of that structure to appear in nature, the universe must provide a real sequence of events capable of creating it. Black holes have at least two pathways supported by strong observational evidence. They can form when the cores of massive stars collapse, then continue gaining mass by drawing in surrounding matter or merging with other black holes. No comparable astronomical pathway has yet been confirmed for white holes. Some physicists have speculated that white holes might have formed in the early universe, when densities and physical conditions were profoundly different from those of today. Yet this remains only a possibility within extended theoretical models. No primordial population of white holes has been directly observed, and the standard cosmological model does not require them to have formed in significant numbers. Even if we assume that some unknown mechanism once created a white hole, the story would still not be complete. An ideal solution may place it in perfectly empty space, where no matter or light approaches, but the real universe has never been so quiet. Gas and dust remain present between the stars. Intergalactic space still contains background radiation, high-energy particles, and light arriving from extremely distant sources. A white hole with mass would continue to curve the space-time around it, allowing external material to be drawn toward it, even though the idealized structure would not permit that material to cross the white hole horizon. This conflict forces the white hole to confront an even greater challenge than the problem of its formation. Even if it somehow appeared, could such a structure survive within a universe where matter and radiation are always in motion? The most dangerous enemy of a white hole might not be a star or planet rushing toward it, but a single, solitary photon drifting silently toward the horizon. Imagine an ideal white hole existing in a region of completely undisturbed space. There are no nearby stars, no drifting clouds of gas, and not a single grain of dust or ray of light approaching it from the outside. In an environment prepared with such precision, the mathematical structure of the white hole could remain intact. Matter and light would travel only outward, while no future directed trajectory would allow anything to pass from the exterior into the interior. But the real universe is never that quiet. Even the dark regions between galaxies are not perfect vacuums. All of space is filled with a cosmic microwave background, the remnant light left behind from the early universe. Its average temperature is only about 2.725 Kelvin, barely above absolute zero, yet it remains present in every direction and continuously travels through space. Alongside it are light from distant galaxies, extremely thin gas, high-energy particles, neutrinos, and gravitational ripples produced by cosmic events. Because it has mass, an ideal white hole would still generate a gravitational field. It would not repel everything like a source of antigravity. A photon, a grain of dust, or a passing cloud of gas could still have its path curved and be drawn closer to the horizon. This is where the structure of the white hole begins to encounter trouble. Gravity pulls external matter inward, while the white hole horizon permits no future directed trajectory from the outside to cross into the interior. These two features do not create a wall that simply throws incoming matter backward. Instead, they force approaching light and matter into increasingly extreme conditions near the horizon, placing ever greater stress on an already fragile region of spacetime. In 1974, physicist Douglas Eardley examined this problem in a paper titled "Death of White Holes in the Early Universe." He showed that classical white holes could suffer from a form of instability that grows extremely rapidly. Even a tiny amount of matter or radiation approaching the white hole horizon could strongly disturb the structure of spacetime and eventually cause the region to become a black hole. To understand this without going deeply into the equations, imagine following a single photon as it approaches the white hole. From a great distance, that photon may carry only a small and almost insignificant amount of energy. Yet, as it enters an increasingly powerful gravitational region, its energy is described differently by observers near the horizon. In the case of a black hole, light emitted near the horizon is usually redshifted as it travels outward, meaning that the energy received by a distant observer is reduced. Near a white hole horizon, the corresponding process involving incoming light can behave in the opposite way. Radiation is shifted toward higher energies as it approaches the horizon, as though its wavelengths are being compressed shorter and shorter. The photon does not need to exceed the speed of light, nor is it crushed by some mysterious force. It continues to move according to familiar local laws. The problem lies in the accumulation of energy created by the way space-time is arranged around the white hole horizon. A disturbance that begins almost imperceptibly can be amplified until it can no longer be treated as a minor change. In general relativity, energy and matter do not merely move across a stage that already exists. They also help determine the shape of that stage. As the energy of radiation near the horizon rises, it acts back upon the curvature of space-time. The structure that once allowed everything to move only outward begins to change beneath the weight of the incoming disturbance itself. If the change becomes strong enough, a trapped region may form. Instead of preserving the white hole horizon, space-time creates a new black hole horizon around the area. Matter from the outside can then move inward, while anything inside can no longer escape. The white hole does not explode like a bomb, nor must it disappear in a brilliant flash visible from afar. It simply loses the causal structure that made it a white hole. One way to picture this is as a surface of water being held in a highly unusual shape. Pumps beneath the surface create a standing wave, with every part of the water balanced precisely. In a perfectly quiet environment, that shape might persist. But the moment a single drop falls in the wrong place, a new disturbance appears, spreads outward, and begins affecting the surrounding regions. If the system is too sensitive, the disturbance does not fade. It continues to grow until the original shape collapses. A classical white hole requires a similarly precise balance. It survives within the idealized solution because every condition in its past has been arranged exactly as required. The real universe, however, constantly introduces new elements that were never part of that preparation. A photon from a distant star, a thin layer of gas, or a small gravitational disturbance could cause the actual history to diverge from the perfectly reversed film. Another way to imagine it is as water being forced to flow upward over a waterfall. In a carefully engineered system, pumps might compel the water to move in this unnatural direction for a time. But if the pressure changes, the power begins to fluctuate, or an obstruction falls into the flow, the water quickly returns to the more stable direction of moving downward. In this comparison, a black hole resembles the more stable direction of flow. Matter in many different states can fall inward without requiring the entire environment to be prepared with perfect precision. A white hole is more like water being forced uphill, able to persist only while the surrounding conditions continue to match a highly specific history. What is remarkable is that an entire star would not need to plunge toward a white hole in order to destroy it. A star would certainly produce an enormous disturbance, but even far weaker radiation could become a serious problem if the white hole survived long enough. The cosmic background radiation may be extremely cold, but it is always present. Light from distant galaxies also continues to pass through every unobstructed region of space. A classical white hole surviving for millions or billions of years would therefore be extremely difficult to reconcile with a realistic astronomical environment. Over such a vast span of time, it would be nearly impossible to keep the surrounding region completely free of matter and radiation. The longer it existed, the more likely it would be to encounter some disturbance, while its structure would remain especially sensitive to those very disturbances. This marks an important difference between white holes and many other astronomical objects. A star can absorb falling gas or dust and continue to exist. A black hole can even grow more massive by consuming matter. For a classical white hole, however, incoming material would do more than alter its mass. It would threaten the very property that makes the object a white hole. This instability was one reason the idea of astronomical white holes gradually lost much of its appeal. A structure that appears in the equations but can barely survive in a real environment is unlikely to become a long-lived object for telescopes to discover. Even if white holes were once created, they may have been transformed so quickly that they never left behind a clear signature. Yet this does not necessarily eliminate every possibility connected to white holes. The instability argument applies mainly to classical white holes that survive for long periods and closely resemble the complete time-reversed image of a black hole. If a white hole appeared only for an extremely brief interval, its surroundings might not have enough time to disturb it strongly enough to destroy it. A flash of lightning does not need to endure for millions of years to be a real event. It only needs to appear for a moment and leave behind light that an instrument can record. In the same way, some modern models do not describe a white hole as a stable astronomical body drifting through space. Instead, they treat the white hole phase as a brief transition during the lifetime of a black hole. In these models, matter collapsing into a black hole does not necessarily end at a point of infinite density. When space-time is compressed to an extremely small scale, quantum effects that are not yet fully understood may halt the contraction or cause it to rebound. A region that once trapped matter inside could then temporarily become one that allows matter to escape. Such proposals do not automatically remove the problem of instability. A white hole emerging from a transition would still have to interact with the external environment. Its lifetime would become a critical factor. If the white hole phase lasted too long, incoming matter could continue amplifying disturbances and prevent the release from occurring. A 2015 study argued that prolonged transitions could be highly unstable, while processes that unfold quickly enough might have a better chance of avoiding part of this problem. But exactly how fast is fast enough still depends on the model. For an observer near the transition region, the change might occur over a short period. To someone watching from very far away, however, the process could appear to last much longer because of the curvature of space-time. Determining how these two measures of time relate to each other is one of the reasons different black hole to white hole proposals can lead to very different conclusions. Some models imagine the white hole phase as a rapid bounce that releases energy in a brief eruption and then disappears. Others suggest that, after a black hole has nearly completed its evaporation, it might leave behind a tiny white hole remnant that appears small from the outside but contains a large interior region. This remnant has been proposed as a possible way to store and gradually release information over a long period, although the idea remains theoretical and has not been confirmed through observation. These two pictures are nearly opposite. In the first, the white hole must act quickly to avoid being choked off by its surroundings. In the second, a tiny remnant must survive for an extremely long time without being destroyed by the same classical instability. The fact that different models lead to such different outcomes shows that humanity still lacks a unified theory of quantum gravity capable of determining what truly happens. The central questions therefore remain unanswered. If a black hole transforms into a white hole, how long does the process take? Is matter released in a sudden explosion or through a prolonged stream of radiation? Would the energy carried away be consistent with astronomical signals that have already been observed? Could the white hole horizon survive long enough to leave a detectable trace, yet remain brief enough to avoid being destroyed by disturbances? No answer has yet gained broad acceptance within the physics community. Quantum transition models are serious attempts to understand what happens when general relativity reaches its limits, but they have not been experimentally verified. They therefore cannot be used to claim that every black hole will eventually become a white hole. What can be said with greater confidence is that a classical white hole would find it extremely difficult to survive in the real universe. It requires an almost perfectly prepared environment, while space is always filled with matter and radiation. A tiny disturbance can be amplified, act back upon space-time, and transform a structure that permits only outward motion into a black hole region that allows matter to fall inward. This instability helps explain why the sky contains so much evidence of black holes yet has revealed no long-lived white hole. But it answers only part of the question. Behind this fragility lies a deeper mystery. Why is it so easy for matter to fall inward, structures to collapse, and energy to disperse, while the reversed process almost never occurs? Perhaps a white hole does not merely lose its struggle against the surrounding environment. It may also run against the direction of time that the universe itself appears to favor. Is a white hole nothing more than a film that remains valid within the equations, yet can almost never be shown in the direction of time followed by the real world? To understand this, we must return to a very ordinary event. A glass can fall to the floor and shatter into many pieces, but those fragments never rise on their own and fit themselves back together. In a quiet room, a glass sits near the edge of a table. A slight bump is enough to make it lose its balance, fall to the floor, and shatter into many pieces. The sound echoes for a few seconds, shards slide in different directions, and the room soon becomes quiet again. Nothing about this scene surprises us. Fragile objects fall, water spills, and broken pieces remain scattered across the floor. What is almost impossible to imagine is the entire process unfolding on its own in reverse. The shards begin sliding toward one another, rise from the ground, and fit back together into an intact glass before returning to their exact place on the table. If we watched such footage, we would immediately know it was running backward without ever looking at a clock. The sequence of events would reveal the direction of time by itself. An intact glass can become a collection of fragments, but those fragments do not reassemble on their own. Smoke can spread throughout a room, but it does not spontaneously gather into a single point and return to the flame from which it came. At the atomic level, however, the distinction between past and future is not always so clear. Many fundamental equations can still describe a system when the motions of its particles are reversed. Two molecules may collide, change direction, and separate, and the same sequence can be imagined running backward while each individual motion still obeys the laws of physics. The difficulty appears only when an enormous number of particles must coordinate at once. For the glass to rebuild itself, every fragment would need to move in the correct direction, at exactly the right moment, and with nearly perfect speed. The air would have to push the shards with extraordinary precision, while vibrations in the floor would need to return exactly the energy they received when the glass struck the ground. If even a tiny part of the process went wrong, the glass could not return to its original state. At the scale of everyday life, so many particles are involved that the chance of all of them accidentally coordinating into the exact reversed history becomes almost non-existent. Entropy helps explain why one direction of events is far more common than the other. It is often described simply as a measure of disorder, but a meaning closer to physics is the number of microscopic arrangements capable of producing the same large-scale state that we observe. An intact glass is a highly special state. Its molecules must be bonded into a particular shape, the walls must have the correct curvature, and every part must occupy its proper position. Only a relatively small group of microscopic arrangements can produce the object we recognize as a complete glass. Once the glass breaks, its fragments can rest in countless different positions. One piece may stop near the leg of the table or slide a few centimeters farther away. Another may land face down, lean to one side, or lie beneath a larger shard. Although these arrangements differ, we describe all of them as the broken state. There are far more ways to produce the broken state than the intact one. When a system is free to move among a vast number of possibilities, it is more likely to reach states that occupy most of the available arrangements. In this sense, entropy is not a mysterious force pushing things toward disorder. It is a consequence of probability. A deck of cards offers a similar picture. When the cards are arranged precisely by suit and value, the deck occupies an extraordinarily special state. After several shuffles, an enormous number of other arrangements may appear. No law absolutely forbids the deck from accidentally returning to its original order, but the number of mixed configurations is so vast that the probability becomes negligible. The second law of thermodynamics, however, does not mean that entropy can never decrease anywhere. A refrigerator can cool the space inside it. A living organism can grow from a single cell, and humans can gather scattered materials to construct a house. These processes simply do not occur within a completely isolated system. A refrigerator requires electricity and releases heat into the room. Living organisms absorb energy from food or sunlight, then release heat and waste into their surroundings. A small region may become more ordered, but when everything else is included, total entropy still tends to increase. In extremely small systems, the story becomes more subtle. In 2002, researchers tracked a tiny colloidal particle held in water by an optical trap. Over brief intervals, they observed some motions in which entropy temporarily decreased, as though the system were taking short steps against its usual direction. Yet when they observed it for long enough and averaged the results across many trials, entropy still increased exactly as the second law predicted. This experiment did not show that a shattered glass could rebuild itself. It demonstrated only that at very small scales, where few components are involved and thermal fluctuations have a noticeable influence, brief reversals can occur. As the number of particles rises to the scale of a glass, a living body, or a star, the probability that the entire system will reverse together falls so rapidly that it becomes almost impossible to observe. Imagine a person moving through a crowd. For a few seconds, several individuals may happen to walk against the general flow. But for millions of people to turn around at once, return to their exact previous positions, and repeat every earlier movement in reverse order would require an entirely different arrangement. The relationship between entropy and information is not merely an abstract idea. In 1961, physicist Rolf Landauer argued that erasing one bit of information cannot occur without producing a minimum amount of heat. In 2012, a research team tested this prediction by using a single colloidal particle as a 1-bit memory inside a trap with 2 stable positions. When the researchers forced the particle to return to one side, an operation equivalent to erasing its previous information, heat was transferred into the environment. During sufficiently slow erasure cycles, the average amount of heat approached the limit predicted by Landauer. The results showed that information is not entirely separate from the physical world. Even forgetting a single bit of data carries a thermodynamic cost. This makes the arrow of time feel more immediate. When an event occurs, it leaves traces in its surroundings. Light is emitted, heat spreads, sound travels through the air, and information becomes recorded in matter. For the entire event to run backward, not only would the main object have to reverse its motion, but every one of those traces would also have to return to its source at the same time. We remember the past but not the future because memories are formed from events that have already left traces. A camera records photons only after they reach its sensor. The brain creates a memory only after signals have passed through its neurons. These recording processes also consume energy and alter the surrounding environment. The arrow of time we experience is therefore closely tied to the increase of entropy. Heat flows from hotter objects to colder ones. Scents spread through the air, and energy capable of doing useful work gradually disperses. The reverse direction is not absolutely forbidden in every microscopic motion, but on a large scale, it would require a degree of coordination that is almost impossible to prepare. A drop of ink falling into a glass of clear water stretches into colored tendrils and spreads until the water becomes nearly uniform. The ink molecules continue moving and colliding, yet there is no reason for all of them to return to a single point. For the original drop to reappear, trillions upon trillions of dispersed molecules would have to choose precisely the right direction at the same moment. Black holes fit quite naturally into this direction of events. Matter can approach them from many directions while carrying vastly different structures. A cloud of gas, a star, or even a planet can cross the horizon if it comes close enough. From the perspective of an outside observer, most of the details of those objects then become hidden. A stable black hole is described externally mainly by its mass, spin, and electric charge. Two objects that were initially very different can still contribute to black holes with nearly identical outward properties. This does not necessarily mean that information has been destroyed, but it does show that the original details are no longer easily accessible once they have crossed the horizon. In the 1970s, Jacob Bekenstein proposed that black holes must possess entropy, and that this entropy is proportional to the area of the horizon, rather than the volume inside it. This was a deeply counterintuitive result. Larger objects are usually imagined as having more space within them, yet the information capacity of a black hole appears to be written on the boundary surrounding it. Earlier, Stephen Hawking had shown that in classical general relativity, the total horizon area of black holes does not decrease over time as long as certain physical conditions are satisfied. This property resembled the second law of thermodynamics so closely that it became one of the foundations of the idea of black hole entropy. The connection is not confined to theory. In 2021, researchers reanalyzed the signal from GW150914, the first gravitational wave event detected from the merger of two black holes. They compared the estimated horizon areas of the two black holes before the collision with the area of the final black hole and found that the data were consistent with the prediction that the total area did not decrease. This was not a direct measurement of entropy, but it showed that a rule deeply connected to black hole thermodynamics could be tested through astronomical observations. When matter falls into a black hole, entropy outside may appear to decrease because that material system can no longer be observed. To preserve the second law, the entropy associated with the black hole must increase enough to compensate. This led to the idea that the entropy of the black hole, combined with the entropy of matter and radiation outside it, must never decrease. A classical white hole seems to require an almost opposite process. From a region that appears relatively simple from the outside, matter and radiation would have to emerge in highly specific states. If it were the complete time-reversed image of a star collapsing into a black hole, what emerged could not be merely a random cloud of particles. Every atom would have to appear at the correct position and with the correct velocity for the reversed history to continue. Streams of gas would need to converge into structured layers of matter. Dispersed heat would have to concentrate again, and nuclear reactions within the star would need to unfold in reverse order. Eventually, the emerging material would have to reconstruct the star and the environment that existed before the collapse began. Such a history would require initial conditions of extraordinarily low entropy. Not only would the white hole itself have to be prepared with extreme precision, but the entire surrounding region would also need to match the reversed film. Light from distant sources could not arrive at the wrong moment. Gas and dust could not introduce additional disturbances, and every outgoing particle would have to carry exactly the required state. This demand is directly connected to the instability of white holes. A single photon that does not belong to the perfectly arranged history could alter the energy near the horizon. Even a small amount of gas from the surrounding environment could prevent the structure from continuing to follow the original time-reversed process. A white hole therefore lacks more than an observed mechanism of formation. It also requires its entire past to be arranged with almost absolute precision. While many different initial states of a star can lead to collapse and the formation of a black hole, only an extraordinarily narrow set of histories could produce the corresponding reversed image. Even so, it would not be accurate to say that the second law absolutely forbids every possible form of white hole. Experiments with microscopic systems show that entropy can temporarily decrease through fluctuations, while the thermodynamics of horizons is far more complex than that of a glass or a deck of cards. When quantum effects become important, the way information is stored and released may differ from classical intuition. If a white hole appeared only briefly as part of a quantum transition, it might not need to reconstruct an intact star that had previously collapsed. Matter and information could be released as radiation or through some other process that is not yet fully understood. No model describing such an event, however, has been confirmed through observation. The most cautious conclusion is that classical white holes do not easily emerge from any ordinary conditions known to physics. They require an exceptionally special arrangement. While the observable universe generally evolves towards states that can be realized in a far greater number of ways, this tendency is present in nearly every experience. Living organisms grow older, fuel is consumed, and useful energy gradually disperses as heat. Light reaches our eyes only after leaving a star, and memories form only after an event has occurred. Countless small processes all point in the same direction, the direction in which total entropy tends to increase. Black holes move with that flow. A star loses its balance, its core collapses, matter crosses the horizon, and many details become hidden. A classical white hole would require the film to run backward, with matter emerging in states precise enough to build increasingly ordered structures. Perhaps this is the deeper reason the two regions can remain symmetrical in the equations while failing to appear symmetrically in nature. Mathematics allows both black holes and white holes to be drawn on the same map. The thermodynamic arrow of time makes one side comparatively easy to create, while the other demands a past that is almost impossible to prepare. On paper, black holes and white holes still face each other like two perfectly balanced doors. In the actual history of the universe, one side is born from dying stars and revealed through light, orbital motion, and gravitational waves. The other remains suspended between mathematics and speculation. Yet the symmetry of the map raises another question. If black holes and white holes appear together within an extended structure of spacetime, could they represent opposite ends of a tunnel connecting regions separated by an enormous distance? That idea leads us to the Einstein-Rosen bridge, a famous structure that is also among the most widely misunderstood concepts in modern physics. Imagine 2 points located very far apart on a sheet of paper. If you travel along the surface, the journey between them must cover the entire distance drawn on the page. But if the paper is folded so that the 2 points move close together, a connection passing through both layers seems capable of shortening the trip. This is the image often used to explain a wormhole, a hypothetical tunnel that could connect 2 distant regions of spacetime. Instead of traveling for thousands of years across the space between the stars, a spacecraft might enter one end of the tunnel and emerge from the other after crossing a much shorter distance. The image is easy to understand, but it can also be misleading. Spacetime is not necessarily a sheet of material resting inside some larger space where it can be folded by hand. The paper only helps us imagine how geometry might create a shorter route between 2 distant regions. It does not explain how such a tunnel would form, whether it would remain stable, or whether matter could actually pass through it. This distinction becomes especially important when discussing the bridge that appears in the solution for an eternal black hole. On a spatial cross-section, 2 distant regions seem to be connected by a narrow throat, yet the fact that they are geometrically related does not mean there is a route between them for light, matter, or human travelers. In 1935, Albert Einstein and Nathan Rosen, 2 physicists working on general relativity, examined a way of connecting 2 regions within the solution, describing the gravitational field around a spherical object that neither rotates nor carries an electric charge. Their goal was not to create a gateway for interstellar travel. They were searching for a way to use space-time geometry to describe matter without placing an infinite point at the center of the model. The structure developed in that work later became known as the Einstein-Rosen bridge. When the ideal black hole solution is extended as fully as possible, 2 exterior regions appear on opposite sides of the map. Between them lies a bridge-like section of geometry, while the black hole region extends toward the future and the white hole region lies toward the past. Looking only at a still diagram, it is easy to imagine an astronaut entering a black hole from one side, crossing the narrow throat, and emerging from a white hole on the other. But a still image is only a single frame taken from a film. It shows what space looks like at one moment, without revealing how the structure changes as time continues to pass. Once the full evolution is taken into account, the bridge does not remain open long enough for light or matter to cross. The throat collapses before any signal can travel from one exterior region to the other. The problem is not that the spacecraft is too slow or its engines too weak. Within this structure, no future directed trajectory exists that can complete the journey. Imagine a corridor clearly shown on the blueprint of a building. Its 2 ends appear to connect separate rooms, but the moment someone steps inside, the exit begins moving away while the walls rapidly close together. The traveler could run at the highest speed allowed and still never reach the other side, because the corridor changes faster than they can move through it. The classical Einstein-Rosen bridge is likewise not a passageway that remains closed merely because our technology is inadequate. It contains no causal path capable of carrying an object from one side to the other. To cross it, a spacecraft would have to follow a direction that light and matter are not permitted to take within that space-time structure. An astronaut crossing a black hole horizon would not see a white hole waiting ahead like an emergency exit. After entering the black hole region, every future directed trajectory leads farther inward. The traveler cannot turn toward the white hole region because the white hole lies in the past of the diagram rather than at a destination somewhere ahead. The 2 regions may appear together on the same map, but that does not make them the 2 ends of a journey. The past and future also appear together on a timeline, Yet someone moving into the future cannot simply step into the past because both are drawn on the same page. There is another important point. The two exterior regions in the eternal black hole solution are not simply distant locations within the same galaxy. They are separate domains that arise within an ideal mathematical structure that has existed in complete form since the infinite past. No observation has shown that real black holes in the universe connect our region of space to a second exterior domain in this way. Black holes formed by collapsing stars also have a different history from the eternal solution. At first, there is an ordinary star. Once the fuel in its core is depleted, the matter contracts and a horizon forms. Before that collapse, there is no pre-existing white hole region in the past, nor a second exterior domain waiting on the other side. An astronomical black hole, therefore, does not automatically come with a bridge leading somewhere else. It can bend light, trap matter beyond its horizon, and strongly influence its surroundings, but there is no evidence that anything falling into it will reappear in a distant galaxy. The supermassive dark object at the center of the Milky Way provides an example. The motions of nearby stars reveal that a mass roughly 4 million times greater than the Sun is concentrated within a very small region. Hot gas and flares near it can be observed, yet no signal has shown that matter crosses the horizon and then emerges somewhere else. The enormous jets seen near certain black holes are not evidence of an exit either. They are produced by gas and magnetic fields outside the horizon. Matter in the accretion disk rotates at tremendous speed, and some of it is guided by magnetic fields into two narrow streams launched near the poles. It is redirected before falling into the black hole, rather than traveling through the interior and escaping again. The Einstein-Rosen bridge must therefore be distinguished from a traversable wormhole. A traversable wormhole, if one exists, would need to keep its throat open long enough for light or a human traveler to pass from one end to the other. It could not contain a horizon blocking the route, a singular region lying ahead, or tidal forces powerful enough to tear apart anything traveling through it. In the late 1980s, a group of physicists studied the conditions that such a tunnel would require. They did not claim to have discovered a wormhole. Instead, they used the equations of general relativity to ask what properties a traversable structure would need to possess. Their results showed that the greatest obstacle would be preventing the throat from collapsing. Ordinary matter carries positive energy and produces gravity, causing the tunnel to contract. To hold it open, most models require a special distribution of energy, capable of resisting that collapse. This hypothetical form of energy is often described as exotic matter. The name may suggest a mysterious substance from some distant place, but in physics, it simply refers to a state with energy properties unlike those of familiar matter. The wormhole's throat would require an effect strong enough to keep space-time open rather than allowing gravity to pull both sides shut. Quantum physics does allow certain effects in which the energy density falls below that of the ordinary vacuum under special conditions. Yet the known effects are generally extremely small, confined to limited regions, and unable to persist for arbitrary lengths of time. There is no evidence that they could be gathered in sufficient quantities to hold open a space-time tunnel large enough for a human traveler. One frequently cited example is the effect that occurs between two metal surfaces placed extremely close together in a vacuum. Quantum fluctuations are restricted differently in the narrow gap between the surfaces than they are in the surrounding space, producing a tiny force that can be measured. This phenomenon reveals that the quantum vacuum is not completely empty, but it does not provide a doorway for constructing a wormhole. The gap between a small quantum effect in a laboratory and a tunnel large enough for a spacecraft is immense. Even if the equations permit such a structure, we still do not know how to create it, keep it stable, or prevent matter passing through from altering the shape of the tunnel. A wormhole could also be destroyed by the radiation traveling inside it. Light passing through the throat might become concentrated or amplified. Matter entering the tunnel could strengthen its gravitational field and cause it to contract. Disturbances that begin extremely small might grow over time, much like the instability associated with classical white holes. Even if the tunnel could be held open, physicists would still have to solve the problem of tidal forces. In an uneven gravitational field, the side of an object closer to the source is pulled more strongly than the side farther away. If that difference became too great, a spacecraft or a human body could be stretched apart and destroyed before reaching the other end. A safe tunnel would therefore need more than mere existence. It would require the right size, shape, and curvature. The journey would have to be short enough, the throat wide enough, and the gravitational forces along the way gentle enough to avoid destruction. Each additional requirement makes such a structure even more difficult for nature to create. A white hole should not be treated as the necessary exit of a wormhole either. A traversable wormhole is usually imagined as having two mouths through which matter can move between two regions. A classical white hole, by contrast, possesses a horizon that allows matter to emerge but provides no future-directed path from the outside into its interior. Both ideas involve the geometry of space-time, but they do not describe the same structure. Similarly, we should not claim that every black hole has a white hole on the other side. The white hole region appears in the idealized solution for an eternal black hole, where the complete structure has already been built into the mathematics. A black hole formed through stellar collapse does not automatically contain such a region. Some models of quantum gravity propose that a black hole could transform into a white hole at a very late stage. In this picture, matter contracts within the black hole without ever reaching infinite density. Quantum effects might halt the contraction and cause a rebound, allowing matter or information to emerge. This would not be a journey through the classical Einstein-Rosen bridge. It would be a transformation in the structure of space-time unfolding over time, and no observation has yet shown that it truly occurs. The fact that a model permits such a process does not mean that every black hole is concealing an exit. The appeal of wormholes comes from the immense distances of the universe. Even the nearest star beyond the Sun lies more than 4 light-years away. With present technology, a spacecraft would require far longer than a human lifetime to reach it. Distant galaxies remain beyond any journey that could be completed through conventional travel. A shortcut through space-time therefore touches a deep human desire to overcome limits, reach distant places without waiting thousands of years, and discover what lies beyond doors we cannot yet open. But the beauty of an idea cannot replace physical evidence. For a wormhole to become a real object, there must be a mechanism capable of forming it, a source of energy able to keep it open, and an observable signature that distinguishes it from a black hole or another compact object. So far, no wormhole has been discovered, and there is no evidence that nature creates tunnels through which matter can travel. The Einstein-Rosen bridge remains deeply valuable because it shows that space-time can possess structures far more complex than ordinary intuition suggests. It helped physicists recognize that a geometric connection is not necessarily a causal passage, while also clarifying the difference between two regions being joined on a map and a real object being able to travel from one to the other. When the full evolution through time is taken into account, the bridge closes before any signal can cross it. An astronaut entering a black hole does not emerge from a white hole, and matter that has passed beyond the horizon has no known escape route into some distant region. But as the image of the tunnel begins to fade, another question remains. If a white hole is not the exit of a bridge passing through a black hole, could our entire expanding universe be viewed as a much larger kind of exit? Did the Big Bang truly resemble matter erupting from a white hole? Or does that similarity exist only in the image it creates? To answer that question, we must return to a time when the universe was still hot and dense, long before the first stars began to shine. Let us turn time back to a very young universe, before there were planets, stars, or galaxies. Space did not yet contain the vast dark expanses scattered with points of light that we see today. Matter and radiation existed in a hot, dense, and nearly uniform state, while tiny variations in density were only the faintest seeds of the structures that would eventually form. As the universe continued to expand, its temperature gradually fell. During the first few minutes, fundamental particles combined to form most of the nuclei of hydrogen, helium, and very small amounts of other light elements. Yet the universe was still too hot for electrons to remain stably bound to atomic nuclei, so light continually collided with charged particles and could not travel very far. About 380,000 years after the expansion began, the temperature had fallen enough for nuclei to capture electrons and form neutral atoms. Light from that period could then begin traveling freely through space. Today, The expansion of the universe has stretched it into extremely weak microwave wavelengths, creating the ancient glow known as the cosmic microwave background. This light is present in every direction and is often described as a childhood photograph of the universe. It is not perfectly uniform, but contains temperature variations of only a few millionths of a degree. Those extraordinarily small differences reflect regions with slightly different densities in the early universe, where gravity gradually gathered matter together to form stars, galaxies, and the immense cosmic web that appeared later. After this ancient light was released, the universe entered a long period before any stars existed. Most matter consisted of neutral hydrogen and helium, while denser regions continued contracting under gravity. The exact moment when the first stars began to shine has not been fully determined, but they must have appeared after the 380,000-year mark, and before the earliest galaxies had formed several 100 million years after the Big Bang. From a hot and nearly uniform state, the universe gradually became a place containing hundreds of billions of galaxies within the region humanity can observe. This entire journey is commonly described by the name Big Bang, yet the term can easily create an inaccurate image: a gigantic bomb exploding at one point in the middle of empty space. An ordinary explosion begins at a particular location and throws matter outward into space that already exists. It has a center and can be observed from the outside. If the Big Bang had happened this way, we might imagine every galaxy flying away from a single point located somewhere within the universe. Modern cosmology tells a different story. The Big Bang was not matter exploding into empty space, but the distance between regions of matter increasing as space itself expanded. There is no single central point from which every galaxy is moving away. Every region of the observable universe was once closer to every other region than it is today. One way to picture this is to imagine small dots drawn on the surface of an inflating balloon. As the surface expands, every dot sees the others moving away. Yet no point on the surface is the center of the expansion. The center of the balloon in this analogy does not represent a real location within the universe. The image merely helps us understand how distances can increase everywhere without requiring a center inside the expanding space itself. Another image is that of raisins embedded in rising dough. As the dough expands, the distance between every raisin increases. None of them needs to fly through the dough from a single center of explosion. The medium between them is expanding. The comparison is still imperfect, but it comes closer to the Big Bang than the image of a bomb exploding in empty space. This creates the first and most important difference between the Big Bang and a white hole. A classical white hole is a defined region located within a larger spacetime. It has a horizon, an exterior region, and in principle could be observed from a great distance as matter emerged from it. The Big Bang has no such exterior region in the current model. There is no location outside the universe where an observer could stand and watch all of space erupt from a doorway. When we trace cosmic history backward, every region of the observable universe becomes hotter, denser, and closer together. We are not approaching a single place, but a shared era that affected all of space. A classical white hole also possesses spherical symmetry around a particular region. If matter emerges, it comes from an area that can be distinguished from its surroundings. The early universe, by contrast, was nearly uniform on very large scales. The cosmic microwave background reaches us from every direction at almost the same temperature, with only tiny variations. There is no evidence of a central direction from which all matter once flew outward. Despite these clear differences, the Big Bang and a white hole share a similarity powerful enough to inspire the imagination. When the trajectories within a classical white hole are traced backward, they appear to begin in an extreme state inaccessible to an outside observer. When the expansion of the universe is traced backward, its density and temperature also rise toward an increasingly extreme condition. In classical mathematics, if we continue far enough into the past, certain quantities may approach infinity at what is commonly called the Big Bang singularity. The word singularity can make it sound as though an infinitely dense, tiny object once existed at a single point and then exploded. But that interpretation goes beyond what the theory actually tells us. A singularity is often a sign that the model being used is no longer capable of describing what happens. General relativity describes gravity with remarkable accuracy on the scales of planets, stars, galaxies, and even the expansion of the universe. But when density and temperature become extreme, quantum effects may no longer be ignored. Because humanity does not yet possess a complete and experimentally verified theory of quantum gravity, we do not know what the universe's earliest state was truly like. The infinity that appears when the equations are extended backward to their limit may not represent an object that ever physically existed. It may simply mark the point where our present map can no longer be continued. Something similar occurs with the singularity inside a black hole. Classical equations predict that contraction continues toward infinite density, but no one knows whether nature truly creates such a point or whether some unknown quantum effect changes the outcome. This resemblance has led some models to suggest that the origin of the universe and the deepest interior of a black hole might somehow be connected. One idea proposes that the universe passed through a period of contraction before reaching an extremely high density, then rebounded and began expanding. In this picture, the Big Bang was not an absolute beginning, but a transition between a contracting universe and an expanding one. Another speculative possibility suggests that a new region of space-time could form inside a black hole. Matter collapsing from a larger universe might not end at a singularity, but instead enter an expanding phase on the other side. To observers living within that new region, the process might resemble a Big Bang, while from the original universe, it would remain hidden behind the black hole's horizon. This is a compelling image, but no observation has shown that our universe exists inside a black hole belonging to another universe. Nor can we look beyond the entirety of our universe to determine whether a horizon surrounds it. The cosmological model used today does not need to assume that the Big Bang was a white hole in order to explain the mega evidence we observe. Cosmic expansion explains why light from distant galaxies is stretched toward longer wavelengths. The hot early universe explains the existence of the cosmic microwave background, while nuclear reactions during the first few minutes explain why hydrogen and helium make up most ordinary matter. The tiny variations within the cosmic microwave background are also consistent with gravity gradually developing slightly denser regions into galaxies and galaxy clusters. This evidence does not reveal what happened at the earliest possible moment, but it allows us to trace the history of the universe from a hot, dense state to the immense structures of today without introducing a white hole horizon. The fact that both the Big Bang and a white hole evoke the image of matter emerging from an inaccessible past is therefore not enough to prove that they are the same. Two stories may begin with similar imagery while unfolding within very different settings. A white hole is a region within space-time, while the Big Bang concerns the early history of all observable space. A white hole has a horizon separating an interior from an exterior, whereas the Big Bang has no defined region outside it. A classical white hole ejects matter from a particular area, while the early universe was nearly uniform and had no central point of explosion. This does not mean that every possible connection between the two ideas has been ruled out. If a future theory of quantum gravity shows that singularities are replaced by a rebound, the structure of black holes and the origin of the universe might be understood in a new way. For now, however, this remains an area of research without a unified answer. The most cautious way to describe it is that the Big Bang shares certain features with a white hole when viewed through the image of time reversal, but it is not a classical white hole in the usual sense. Calling the entire universe a white hole may create a compelling comparison, but it is not a conclusion supported by observational proof. The remaining gap in our knowledge lies in the era before the oldest light humanity can observe. The cosmic microwave background gives us an image of the universe when it was about 380,000 years old, not at its first moment. Before then, matter and light interacted too strongly for the universe to be transparent to electromagnetic radiation. Modern instruments can measure traces from those early periods, examine the abundance of light elements, and map the tiny variations in the cosmic microwave background. Yet, they cannot directly observe the state where general relativity begins to lose its ability to describe what is happening. This darkness leaves room for many models, but it also requires science to maintain a clear boundary between possibility and evidence. The Big Bang should therefore not be used as proof that white holes exist. It shows only that nature once passed through a state in which matter, radiation, and space itself evolved in ways very different from those we see today. The resemblance may help us ask questions, but it cannot replace measurement. If white holes cannot be clearly recognized in the origin of the universe, perhaps they do not belong at the beginning of the story. Another possibility is that they appear only at the distant end of an object already existing in the universe today. Imagine a solitary black hole drifting through the far future, long after the nearby stars have gone dark and almost no matter remains for it to consume. According to classical physics, it could continue existing in darkness. But when quantum effects are taken into account, the black hole may slowly begin to lose energy and mass. If that process continues to its final stage, what will remain? Will the black hole disappear completely into radiation, leave behind a tiny remnant? Or could the space-time within it rebound into a region that allows matter only to escape? This question carries our journey to the point where general relativity begins to confront its own limits, where a black hole is no longer seen as a doorway that lasts forever, but as an object that may age, gradually lose mass, and move toward an ending that no one yet fully understands. Imagine the universe in a future so distant that the familiar night sky no longer exists. Nearby stars have gone dark. The gas and dust that once drifted between stellar systems have grown sparse, and galaxies are slowly fading into darkness. Within that cold emptiness, a solitary black hole continues to exist in silence, with little matter left to attract and almost no visible trace beyond its own gravitational field. According to classical general relativity, once a black hole has formed, it can continue to exist indefinitely as long as nothing from the outside changes it. The event horizon remains a one-way door, while everything that has fallen through stays hidden from the external universe. But this picture changes when quantum fields are considered within the curved space-time surrounding the black hole. During the 1970s, a British theoretical physicist studied the relationship between gravity, thermodynamics, and quantum mechanics. His name was Stephen Hawking, and his most famous result showed that black holes are not completely black. To a distant observer, the region around the horizon can produce an extremely faint stream of thermal radiation, causing the black hole to lose energy and mass very slowly. This prediction is now known as Hawking radiation. The process is often illustrated as a pair of particles appearing near the horizon, with one falling inward while the other escapes. This image may help convey the general idea, but it is not a complete description. A more accurate understanding is that the quantum vacuum is not entirely empty, and quantum fields respond to curved spacetime in such a way that a distant observer detects a spectrum of radiation with thermal properties. The energy carried by this radiation does not appear for free. As radiation transports energy away, the mass of the black hole must decrease by a corresponding amount. This loss of mass is called black hole evaporation. Although it is nothing like water evaporating from a surface. A black hole has no layer of hot material boiling away. The effect arises from the relationship between quantum fields and the horizon itself. A black hole's temperature is inversely related to its mass. The larger the black hole, the colder it is, while smaller black holes are hotter. A black hole with roughly the mass of the Sun would have a temperature of only about 0.06 of a millionth of a Kelvin, or roughly 60 billionths of a degree above absolute zero. By comparison, the universe's present background radiation has a temperature of about 2.7 Kelvin, tens of millions of times warmer. This means that stellar mass black holes in the universe today are not simply losing energy. They also exist within an environment filled with radiation and may absorb more energy than they emit through Hawking radiation. Because the predicted signal is so faint compared with the surrounding radiation, no telescope has directly measured Hawking radiation from an astronomical black hole. Only in the extremely distant future, after space has continued expanding and the cosmic background has cooled below the temperature of the black hole, could energy loss clearly begin to dominate. From that point onward, the black hole would slowly become lighter, although the initial rate would be almost impossible to notice, ignoring anything else that might fall into it. A black hole with approximately the mass of the Sun would require about 1067 years to evaporate. That is the number 1 followed by roughly 67 zeros, so much longer than the universe's current age of nearly 13.8 billion years that every familiar timescale becomes meaningless. A supermassive black hole would survive far longer still, because evaporation time increases extremely rapidly with mass. For most of its existence, the black hole would change almost imperceptibly, but as its mass decreased, its temperature would rise, and its radiation would become more intense. A process that began with unimaginable slowness would gradually accelerate. The smaller the black hole became, the hotter it would grow. The hotter it became, the faster it would lose energy, and that energy loss would make it smaller still. The final stage could be completely different from the immense lifetime that came before it. A black hole reduced to an extremely small size might release much stronger radiation over a short interval, but this is precisely where our present equations begin to lose their reliability. General relativity describes space-time remarkably well on large scales, while quantum mechanics describes the microscopic world with extraordinary precision, yet humanity still lacks a complete theory capable of combining both in a region of extreme gravity. The problem is not only how the black hole disappears, it also concerns everything that fell into it throughout its lifetime. Imagine dropping a book into a fire. The form of the book disappears as the paper becomes ash, smoke, and heat. Yet, in principle, the states of the particles within the smoke and ash still carry the influence of the original structure. The information has been scrambled so thoroughly that recovering it would be almost impossible. But according to quantum theory, it should not simply vanish from nature. Now replace the fire with a black hole. The book crosses the horizon, carrying information about every page, every molecule, and every quantum state within it. If the black hole lasts forever, that information may remain hidden behind the horizon. But if the black hole eventually evaporates completely, and the radiation that escapes is nothing more than a perfectly random thermal stream containing no trace of what once fell inside, then the original information appears to have been erased from the universe. This conflict is known as the black hole information paradox. In a paper published in 1976, Hawking argued that complete evaporation could lead to a fundamental loss of information, a conclusion that conflicts with the usual quantum mechanical description of how a closed system evolves. Over the following decades, physicists proposed many possible solutions. One possibility is that Hawking radiation is not completely random, but contains extraordinarily subtle correlations through which information is gradually returned to the outside. Another suggests that our understanding of the horizon must be modified once quantum effects are included. Other models propose that the black hole never disappears entirely, but leaves behind an extremely small remnant, capable of storing the information. There is also a more radical possibility. The collapse within the black hole may not end at a singularity, but instead transition into a white hole phase. Inside a classical black hole, matter that has crossed the horizon continues into a region of ever-increasing curvature. If general relativity alone is used, this process leads to a singularity, where density and curvature approach infinity. Yet, an infinite value may not represent a real physical object. It may instead signal that the classical theory has been pushed beyond the limits of where it can be applied. Some models of quantum gravity propose that when space-time is compressed to an extremely small scale, new effects may prevent the contraction from continuing. The interior would not collapse into an infinitely dense point, but would instead undergo a transition resembling a bounce. Afterward, the structure that once directed every trajectory inward could transform into one that guides trajectories outward. One way to imagine this is as a ball being compressed. In a simple classical model, it continues shrinking without ever reaching a limit. In the quantum metaphor, the material of the ball develops a kind of elasticity that appears only under extreme compression, causing the contraction to stop and reverse. Space-time, however, is not made of rubber and contains no literal spring. The image of a bounce merely illustrates a mathematical possibility, not a mechanism that has been observed. In this approach, the black hole region, where all future-directed rays of light are forced inward, is called a trapped region. After the transition, it could become a region where all future-directed light rays point outward, sometimes called an anti-trapped region. This is the feature that most closely resembles a white hole. One of the greatest difficulties is time. For matter falling inside, the change from contraction to rebound might occur over a relatively short interval. But from a great distance, The curvature around the horizon could make the entire process appear to last far longer. An event that happens quickly inside might therefore become visible outside only after a period vastly exceeding the current age of the universe. The models do not agree on when the transition would occur. Some suggest that a black hole could become a white hole before completing its evaporation. Others place the transformation at the very end, when the external mass has fallen to an extremely low value. In the second case, the remaining object might appear tiny from the outside while still containing a large interior region formed throughout the black hole's long lifetime. One group of quantum gravity researchers has proposed that a black hole could undergo quantum tunneling and become a white hole remnant. In their model, the remnant has very little mass, but an interior large enough to store information, which it then releases extremely slowly. This is a serious attempt to describe the complete life cycle of a black hole, but no observation or experiment has confirmed that such a process occurs in nature. The remnant idea addresses part of the problem, but immediately creates new questions. If the object has only a very small mass, how can it maintain such a large interior? How can information escape without releasing too much energy over a short period? Could this tiny white hole survive disturbances from its surroundings, or would even one incoming photon force it back into a black hole state? Some studies suggest that special quantum states might allow the remnant to remain stable longer than a classical white hole. Others emphasize that instability, thermodynamics, and the possible production of enormous numbers of remnants remain serious obstacles. Even the lifetime of such a remnant is uncertain because different calculations can produce dramatically different results. If the transition occurred as a rapid bounce, the released energy might create a brief flash. But if information returned slowly through a long-lived remnant, the signal could be so faint and prolonged that it would be nearly impossible to recognize. Both possibilities depend on untested assumptions about the behavior of space-time at extremely small scales. There is also the question of causality. A black hole to white hole transition must ensure that matter does not appear before the event that caused it. It must also remain consistent with the laws of thermodynamics and avoid allowing information to be copied in ways forbidden by quantum mechanics. If even one of these conditions fails, the model cannot describe nature. For this reason, we cannot say that black holes will certainly turn white. Hawking radiation is a major prediction of quantum field theory in curved spacetime, while the transition into a white hole belongs to unconfirmed models of quantum gravity. The two ideas are connected in some scenarios, but the first does not automatically prove the second. What we currently know is that black holes have temperature, possess entropy, and can, in principle, lose mass. What remains unknown is how the final stage of that process unfolds. A black hole may evaporate completely and return information through subtle correlations within its radiation. It may leave behind a remnant, or the space-time inside it may undergo a transition that, from far away, resembles the birth of a white hole. Let us return to the solitary black hole in the distant future. After a span of time longer than any civilization could imagine, it has lost nearly all of its mass. The horizon has contracted, the temperature has risen, and its final moments are approaching a realm where our present theories no longer provide the same answer. It may disappear in one final release of radiation. It may stop as a tiny remnant, or the doorway that once allowed passage only inward may, for one quantum moment, become a doorway that permits passage only outward. No one today knows which path nature will choose. But if a white hole truly emerged from the death of a black hole, what would our telescopes see? The answer might be hidden within brief flashes across the sky. Yet a mysterious signal has never, by itself, been proof of a white hole. Inside a radio observatory in the middle of the night, the sky does not appear as visible light, but as streams of data continuously moving across computer screens. Most of the time, the signals change only slightly, following the familiar rhythms of distant sources, but every so often, an extremely powerful radio pulse emerges from the background noise, lasts less than the blink of an eye, and then disappears. Some of these pulses endure for only a few thousandths of a second, yet they can carry an enormous amount of radio energy. They are known as fast radio bursts, brief flashes of radio waves that usually arrive from galaxies millions or billions of light-years away. In a remarkably short interval, some events can release as much energy in radio waves as the sun produces over a far longer period. When the first of these signals were detected, their origin was completely mysterious. There was no clear image of the object that had produced the pulse, because the signal was so brief, and its original position was often poorly defined. Many hypotheses appeared, ranging from unusual neutron stars and black holes to cosmic collisions and physical processes that had never before been observed. Among them was the idea that a black hole near the end of its life might rebound into a white hole, releasing matter or energy over an extremely short period. Depending on its mass and the way the transition unfolded, the hypothetical signal might appear as radio waves, gamma rays, or an eruption across several energy bands at once. The resemblance is compelling. A dark object that survives for an immensely long time and then suddenly releases energy could produce a brief flash resembling the signals telescopes already detect. But the fact that a model can produce a certain kind of signal does not mean that every signal of that kind is evidence for the model. The sky contains many objects capable of producing violent eruptions without requiring a white hole. One of them is a magnetar, a type of neutron star with an extraordinarily powerful magnetic field. A neutron star is the ultradense core left behind after the death of a massive star, capable of containing more mass than the Sun within a sphere only about as wide as a city. A magnetar's magnetic field can be trillions of times stronger than Earth's. Sudden changes in its crust or magnetic structure can release tremendous energy, producing flashes of X-rays, gamma rays, and radio waves. For this reason, magnetars have long been considered one of the most likely sources of at least some fast radio bursts. An important breakthrough came on the 28th of April 2020. Observatories detected an exceptionally bright radio pulse from a magnetar within the Milky Way. The object is catalogued as SGR 1935 plus 2154. At nearly the same time, X-ray telescopes recorded an eruption from the very same source. The coincidence between the radio signal and the X-ray burst showed that an active magnetar can produce at least some phenomena resembling fast radio bursts. It was the first time such a signal had been clearly connected to a specific source within the Milky Way, reducing the need to invoke more exotic explanations for every powerful radio flash. This discovery does not mean that all fast radio bursts come from magnetars. Some sources repeat many times, while others have been observed only once. They also appear in different kinds of galaxies and environments, suggesting that more than one mechanism may produce them. Nevertheless, the 2020 event demonstrated that at least one known natural source can create a signal once considered completely mysterious. This is an important lesson in the search for white holes. An unexplained flash does not automatically prove the existence of a new object. Before choosing the most unusual hypothesis, astronomers must determine whether neutron stars, magnetars, stellar collapse, mergers, or known processes surrounding black holes could produce the same signal. Gamma rays present a similar problem. They are an extremely high-energy form of light, often associated with the most powerful explosions in the universe. Long-duration gamma-ray bursts are commonly linked to the deaths of very massive stars when their cores collapse and jets moving close to the speed of light pierce through the outer layers. Many short bursts, by contrast, are associated with the merger of two neutron stars or of a neutron star and a black hole. Because known astronomical mechanisms can produce both short and long gamma-ray flashes, an unusual burst cannot immediately be called evidence of a white hole. Even its duration is not enough to determine its origin. An event lasting less than 2 seconds is usually placed in the short burst category, but some cases have shown that classification based on duration alone can be misleading. To prove that white holes exist, physicists would first need a model that makes specific predictions before the observations are made. The model would have to state clearly how long the signal should last, how much energy it should carry, which wavelengths should dominate, and what accompanying signatures should appear. If a black hole rebounded into a white hole, would the process produce a single pulse or a series of repeated events? Would the energy be released all at once, or leak out over a long period? Would heavy matter emerge with it, or only radiation? Would the signal depend on the original mass of the black hole? These questions must be answered clearly enough for observations to reject the model when the results fail to match its predictions. A prediction made in advance is far more valuable than an explanation adjusted after an event has already occurred. If a model can be altered freely to fit every flash in the sky, it becomes almost impossible to test. A strong scientific hypothesis must accept the possibility of being ruled out when the data do not follow its predictions. The observed signal would then need to be difficult to explain through known sources. Magnetars, supernovae, mergers of compact objects, accretion disks around black holes, and relativistic jets would all have to be examined. Only when conventional mechanisms repeatedly fail, while a white hole model explains several features at once, would the possibility of a new object become more convincing. A single flash would rarely be enough. Strong evidence might require several observational channels to record the same event, like independent witnesses describing one phenomenon from different perspectives. Radio waves can reveal a process involving the coordinated motion of electric charges. X-rays and gamma rays expose regions of extreme temperature or energy. Visible and infrared light help identify the surrounding environment, the host galaxy, and any material expelled by the event. Each band of radiation contributes a different part of the story. Gravitational waves provide an entirely different kind of information. They are ripples in the structure of space-time, produced when extremely massive objects move violently or merge. The shape of the signal can reveal the mass, spin, and properties of the final object without depending on any light it emits. Neutrinos are particles with almost no electric charge that interact only very weakly with matter. They can escape from dense regions that light struggles to cross, providing traces of hidden high-energy reactions. Observatories have searched for neutrinos arriving at the same time as fast radio bursts, but so far, no connection has been strong enough to establish a common source. If a radio burst, gamma rays, gravitational waves, and neutrinos all arrive from the same location, at matching times and with energies consistent with a model's predictions, the evidence would be far stronger than any single signal alone. This method is known as multi-messenger astronomy, because each kind of signal acts like a messenger carrying a different part of the same event. A remarkable example occurred in 2017, when gravitational waves from the merger of two neutron stars were detected, followed by a gamma-ray burst only about 2 seconds later. Telescopes continued observing the light from the ejected material for days and months afterward. Together, these observations helped confirm the origin of at least one class of short gamma-ray bursts without requiring a white hole hypothesis. Not every hypothetical white hole, however, would necessarily appear as an explosion. If a white hole survived long enough to exist as an astronomical object, distinguishing it from a black hole could be even more difficult. Both would possess mass, bend light, and influence the gas surrounding them. From a sufficient distance, the external gravitational field of an ideal white hole could resemble that of a black hole with the same mass. Stars could still orbit it. Light could still be deflected, and gas could still be drawn closer. Observing distant orbits alone might not be enough to reveal the difference. The distinction would lie near the horizon. A black hole allows gas to cross the boundary and disappear from observation. A classical white hole contains no future-directed path that carries external matter into its interior. If gas continued to be pulled inward by gravity but could not cross the white hole horizon, it might accumulate, collide, or emit radiation differently from gas accreting onto a black hole. The specific predictions, however, depend heavily on the model. A classical white hole is already highly unstable, so incoming matter could rapidly destroy its structure. A quantum white hole that existed only briefly might not survive long enough to create a clearly observable accretion environment. For this reason, no single observational image has been accepted as a definitive fingerprint of a white hole. The clearest images currently available from regions near a horizon come from a network of radio telescopes spread across several continents, working together as an instrument nearly the size of Earth. This network is known as the Event Horizon Telescope. In 2019, the network released an image of the supermassive object at the center of the galaxy, Messier 87, commonly known as M87. In 2022, another image was published of the object with a mass roughly 4 million times that of the Sun at the center of the Milky Way, known as Sagittarius A. Both appeared as dark regions surrounded by glowing rings of hot gas. These images do not photograph the event horizon directly as a physical surface. The darkness is a shadow created as gravity bends light and traps some photons. The size and shape of the glowing rings agree reasonably well with the predictions for black holes in general relativity. This does not prove with absolute certainty that every alternative model is wrong. Current images still have limited resolution, while the gas and magnetic fields near these objects are extremely complex. Yet the data have revealed no feature that would require scientists to replace the black hole explanation with a white hole. Gravitational waves can test the question from another direction. After two compact objects merge, the final object vibrates briefly before settling into a stable state. The signal is often compared to the sound of a bell after it has been struck, with its frequencies and rate of fading determined by the object's structure. If the final object is a black hole with an absorbing horizon, the signal is predicted to fade in a particular way. If it instead possesses a reflective surface or some other structure near the expected horizon, part of the wave could bounce back and create weaker signals arriving later. These hypothetical signatures are often called post-merger echoes. Some analyses have suggested that certain datasets may contain echoes, but the evidence has not been convincing enough, and the results have not remained consistent across different methods. The latest examinations of data from multiple mergers have still found no reliable evidence of echoes or any clear departure from the predictions of general relativity. Even if echoes were confirmed in the future, they would not automatically prove the existence of a white hole, an unusual surface, a quantum structure near the horizon, or other effects could produce similar signals. Observations would need to distinguish among several competing models before identifying the cause. Another search strategy is to monitor eruptions with no clear precursor. If a dark object remained at one location for a long time, and then suddenly released energy without an accompanying supernova, magnetar, or merger, the event could become an intriguing candidate, but a single case would still not be enough. An instrument might experience interference, the position could be determined incorrectly, or a familiar source might simply be too faint to detect. Researchers would need many events with similar characteristics, distributed in a way consistent with a population of objects and following a clear relationship among energy, duration, and distance. If a model predicts that black holes of a certain mass will rebound after a specific length of time, the observed eruptions must reflect that pattern. Lighter and heavier sources would need to produce measurably different signals. Only when the same model can explain the duration, energy spectrum, and number of events would it begin to become persuasive. Science does not confirm an object simply because it is mysterious. An unexplained signal shows only that current knowledge or data remain incomplete. It does not automatically become evidence for the most dramatic hypothesis. The history of astronomy has repeatedly shown that phenomena once considered entirely new were eventually explained by known objects behaving under extreme conditions. Neutron stars existed only in theory before they were discovered through their regular radio pulses. Fast radio bursts once had no clearly identified source, but at least some are now connected to magnetars. This does not make the mysteries any less compelling. On the contrary, it reveals the value of waiting for several independent lines of evidence before reaching a conclusion. If white holes truly exist, their signatures must meet the same demanding standards that transformed black holes from mathematical solutions into accepted astronomical objects. The sky remains filled with brief flashes. Every night, observatories record radio pulses, X-rays, gamma rays, and gravitational waves arriving from distant regions. Each signal is a question, but most of those questions may ultimately be answered by neutron stars, stellar remnants, merging matter, or gas moving through powerful gravitational fields. A white hole will truly emerge from the equations only when a signature appears that no known source can produce, while also matching a clear prediction made in advance. The result would then need to be repeated, tested by multiple instruments, and confirmed through several independent kinds of signals. So far, no observation has met that standard. Images near horizons remain consistent with black holes. At least some radio bursts have been traced to a confirmed magnetar source, and gravitational wave data have revealed no widely accepted signature of a white hole structure. White holes therefore remain possibilities within certain solutions and physical models. They may help humanity explore the limits of relativity, thermodynamics, and quantum gravity, but they are not yet astronomical objects that have been found in the sky. Perhaps one day, among millions of fleeting signals, a flash will carry features that no magnetar, supernova, or merger can explain. Until such an event appears and is repeatedly verified, the doorway that opens only outward will remain suspended at the boundary between mathematical possibility and an unseen reality. After this long journey through invisible boundaries, maps of space-time, and hypotheses at the limits of physics, the white hole still has not emerged as an object we can point to in the sky. It appears most clearly on paper, within the symmetrical part of an idealized solution, where black holes and white holes stand on opposite sides of time like two doors governed by opposing rules. One side accepts everything that enters and closes off every path of return. The other allows matter and light to escape, but prevents anything outside from crossing in. The symmetry is so elegant that it is easy to believe that if nature creates black holes, it must also create white holes somewhere. But equations are not lists of celestial objects that must exist. Mathematics tells us what can be described without immediately contradicting the laws being considered. The universe imposes stricter demands. A structure must have a way to form, survive disturbances from its surroundings, and persist long enough to leave a detectable trace. It is at these stages that the classical white hole begins to drift away from the observable world. The death of a massive star can produce a black hole without requiring every particle of matter to be arranged with perfect precision. When the energy supporting the core begins to fail, gravity takes control, and the collapse continues on its own. Mergers between compact objects can also create larger black holes, leaving behind gravitational waves that instruments on Earth are able to record. The reverse direction would require a completely different history. Matter would have to emerge from an inaccessible region of the past, travel outward in exactly the required configuration, and avoid every influence that did not belong to that reversed film. Even a thin stream of gas or a ray of light arriving at the wrong moment could destabilize the white hole horizon. That fragility brings us back to the arrow of time. A falling glass can shatter in countless ways, but for it to rebuild itself, every shard, every current of air, and every vibration in the floor would have to return to its previous state with almost perfect accuracy. Microscopic laws may sometimes allow motion to be written in reverse, but on large scales, nature almost always follows the direction with overwhelmingly more possible outcomes. A white hole is therefore not only a question about gravity, it also touches a deeper mystery. Why do the past and future appear so different in our universe, even though many fundamental equations show no obvious preference between them? We remember what has happened, but not what is yet to come. Light carries the image of a star only after leaving it. Heat spreads, fuel is consumed, and the traces of every event gradually become written into the environment. Time is not experienced only through clocks. We feel it through changes that do not easily reverse. Within that flow, the black hole has a more natural place. The white hole resembles a scene in which every individual motion may be valid, yet the entire set must be prepared with a degree of precision so extreme that it is almost impossible to arise by chance. This does not mean the door has been completely closed. When matter inside a black hole reaches extraordinarily high densities, general relativity is no longer sufficient to continue the story. A theory capable of uniting gravity with quantum mechanics may reveal that the singularity is not the end, but a sign of a transitional phase that we do not yet understand. Some models allow the contraction to stop and rebound. Information once hidden may be released, while a region that permitted passage only inward might temporarily become one that allows passage outward. Yet this remains a possibility under investigation, not an observed fate of black holes. The answer to the question of white holes is therefore not a simple declaration. They appear in certain valid solutions of general relativity. No astronomical object has yet been observed and confirmed as a white hole. The possibility that a black hole may enter a white hole phase still belongs to untested models of quantum gravity. These three layers must remain separate, because the boundary between what is known and what is only imagined is precisely where science preserves its strength. An unexplained signal does not automatically prove the most extraordinary hypothesis. At the same time, an unproven idea is not necessarily meaningless. It may expose the limits of a present theory, inspire a new measurement, and compel humanity to ask questions no one had considered before. That may be the deepest meaning of the white hole. It reminds us that validity in reasoning is not the same as existence in nature. Between an elegant equation and a real celestial object lie the entire history of the universe, its initial conditions, the problem of stability, and the demand for observational evidence. Science moves forward not by turning every possibility into a fact, but by keeping imagination broad while holding evidence to the strictest standard. In a future more distant than any civilization could ever wait to see, a solitary black hole may slowly lose mass within a universe that has become almost completely dark. As its horizon contracts toward unimaginably small scales, our present equations will no longer tell us with certainty what happens next. Perhaps it will dissolve into radiation, perhaps a remnant will remain, or perhaps space-time will open in a direction no telescope has ever seen. The white hole, therefore, remains suspended between two possibilities. It may be an extraordinarily rare celestial object waiting to be discovered, or merely the perfect reflection that mathematics places behind the black hole, a doorway that can be drawn on the map, but that the universe has never built. Sometimes, it is the doors that have never opened that help us understand the boundaries of the world in which we live.